So in this part, actually, I will introduce what we're going to talk about, which is how Incentivai actually works and what it does. So first of all, I will briefly introduce a problem, an example problem, which will give a bit more context. Then we'll talk about how it works, and then we'll go through a very quick and simple case study to give it a bit more context. So let's talk about the economics of news services. Like, what do I mean by that? So let's say, how do news services work today in the world? So let's say what we want for the end effect to be is for everyone to have near free access to the news. So this is kind of what we already have today on the internet. And there are different incentives in those systems. So there are some actors who are, advertisers or lobbyists, or there are users who want to be engaged with the content, and there are also parties that compete for that user engagement. But we also know that there are some side effects, like fake or inaccurate news or biased news. And what's interesting is that we can kind of look at this setup from a mechanism design point of view. So if we flip some words, we can see that if we say that our goal is to have that, those are our different mechanisms that we can use. So the different things we can change about our system, and those are the problems that we want to avoid, right? So yeah, so this goes back to these multiple objectives, right? So this is our objective, but those are also our objectives. So things that we don't want to see in the system, and so if we were to actually try and set it up, what we would say is, we want whatever system we have for our news validation, we want it to be unbiased or decentralized. So we want to run it maybe on a public blockchain. And for news validation, we could use this concept of wisdom of the crowds. And for that, we would use prediction markets. So so let's do like a thought experiment of how this could actually be implemented. So we could build a plugin in Chrome. Like, I'm sure there are lots of teams working on something similar already. You have a plugin on Chrome, and whenever you read a piece of news or a tweet and you have a bit of information, you can highlight it and start a prediction market on it, and people immediately start staking money on whether this is true or not. And this kind of validates your news. So now whoever has this plugin and reads news, they get a bit of information about what the consensus thought the true value should be, or how reliable it is, or maybe what the reputation of this particular publisher is, or this particular person on Twitter is. And an interesting twist to add to that would be if we added an option for the publisher of the information, or the person who tweeted, to stake some of their own money on what they said, to actually put their money where their mouth is, and then we could have them actually add a bit of a proof to the tweet, or maybe to the blog post, that they actually stake the money, and then we can see what the consensus thought about that news, what the publisher's reputation is, how often they stake their money, how often that money was lost afterwards. So I don't know. To me, that sounds pretty interesting, the system. But I would argue that this thing would be extremely difficult to build, and not from the technology perspective, because I think all technology is there to build it, but from the mechanism design perspective, to getting the economy right. So what do I mean by that? Lots of potential issues that might arise. So maybe you find out that users don't want to participate at all, so they're not motivated to do the validation of the news. So one potential solution would be to try and increase the expected reward for the users. But maybe now the validators would set up, or the users would set up bribes to bribe the validators and have their fake news validated. So maybe what you could do is try a different reward distribution. But now maybe users might do what miners do, so set up voting pools and delegate their votes to someone else to save time. And that kind of breaks down our wisdom of the crowds assumption. So maybe you could identify user groups that consistently vote the same way, and maybe you can penalize them, or maybe you can downweight their votes. But now you might have just a global problem, that your whole population of users is biased in a certain way, and that again affects the validation of the news. So maybe what you could do is you could identify those groups of users that constantly answer in this or validate the same way facts on the same topics, and you could maybe penalize them or reduce their reputation and so on. But the point of this is that there are lots of potential issues and lots of potential solutions for each one of them, and it's extremely difficult to consider it all. So why? Because we have these multiple objectives, right? So we want the news to be validated, but also for the system to be properly incentivized, and so on and so on. So we have multiple objectives and multiple different mechanisms to try and achieve that, and each mechanism with its own parameters. And what makes it even harder is that there are these complex dependencies. So whenever you change one aspect of the system to help one objective, it might ruin all the other ones, right? So it's kind of like solving the Rubik's Cube, right? When you have all these 6 sides and you want to get them right all at the same time, and you can make all these different moves, but then each move that helps you on one side might ruin all the other ones. So it's very, very difficult. And on top of that, the outcome for us here is really unobservable, right? So it's very difficult to tell, as we've said before, what a particular change to your incentive structure might result in terms of the long-term resultant behavior, right? That's the very difficult problem that we started with. So yeah, so that kind of defines the very, very tricky problem that we're dealing here with. And so let's now talk about where incentivized solution kind of places itself in the framework of building cryptoeconomic systems. So we usually would start here, which is our desired behavior, right? So whenever you're building a cryptoeconomic system, something like Golem, for example, those systems often can be boiled down to what I like to call like a kind of a marketplace, right? So there will be one group of users that wants to do some work or provide some service for money, and there would be another group of users who wants to pay money to have that service provided to them. In the case of Golem, that would be computation. In the case of Ocean Protocol, that could be access to data or access to machine learning models and so on. And then on top of that, you have the fact that Golem is not just at the AWS because it's also decentralized. So the desired behavior would be around many different aspects, multiple objectives like the demand and supply for the computational power, or incentivizing the computation to be done correctly, and so on. So that would define the desired behavior for your particular system. And then what you would do is you would design a mechanism design an economy which hopefully incentivizes that behavior. And once you have your mechanism, the next step is to obviously encode it in some sort of smart contract programming language. And you obviously want to do it without any bugs, and also such that what the smart contract does is exactly what you encoded in your mechanism. Well, hopefully today we have many different methods to ensure that that's done correctly, like formal verification or auditing and so on. And then once we have our smart contracts that are hopefully bug-free, then still, in order to see what the resultant behavior is, what we need is a large-scale deployment in the real world, when there's lots of users and lots of money involved, so that we really see what the resultant long-term behavior is. And then, obviously, the goal of the game is to have the resultant behavior to be as close as possible to the desired one. And that's kind of where Incentivai is, because Incentivai uses simulations to kind of go from your mechanism here. So before you even do the work of encoding the smart contract, just from the specification of your mechanism to approximate and try to predict what the resultant behavior would be, and so that ahead of the time you can optimize your mechanism and only then encode it in your smart contracts and deploy. So let's go into how it actually works. So you would start with your smart contract or even your mechanism specification even before you have your smart contract. And you represent it as an environment. And it's an environment in like a reinforcement learning sort of way. So you can think of it as a world with many agents in it. And at any point in time, agents can observe what the state of the world is and what the different actions they can take. And you can think of those actions as like the different functions in your smart contract ABI. And then what happens is at each timestamp, agents observe the state of the world and observe what the possible actions are. And then the agents use the model of the world that they have to approximate which action would be the best for them, given whatever objective function was set up for them. And then based on that, agents would step by step each choose their optimal action. And then what you do is you kind of take a step back and you look at what the emerging resultant behavior of the whole population of agents is based on those individual decisions. And as you remember, what we also mentioned before is that in the real world, those agents are people. So what we want to also include is potential like ideas from behavioral economics or non-rational behavior, something like users being risk-averse or users optimizing for short-term rather than long-term and so on. So what we would do then is you would include this behavioral model such that the actual choice of actions taken by agents is affected by what we assume about what drives their behavior, in what way they're non-rational, and so on. And it's quite useful to now kind of think back to what we talked about in the first part, where we talked about these hyperparameters that are in our control, and then these parameters that are out of our control, which is what happens after we deploy, right? So the hyperparameters that are in our control, like this is how we set up our system. Like those are our hyperparameters. Like this is what we decided on, and that's encoded in the environment, right? And then the assumptions about agents' motivations, which was the other input to the black box, that's what sits in the behavioral model, and some of it also in the environment, right? But it's useful to kind of identify those two items, that that it's the hyperparameters of our system that are defined in the environment, and then the parameters, and then the assumptions about the agents which are in the behavioral model. Okay, so now let's go into a very simple case study, which will show off kind of how it actually works and how you can actually use it. So I called it a vanilla prediction market, but actually a more accurate way to say would be a decentralized oracle, and with no commit review scheme. So we're going to assume that all the votes are public. So what we want to do is for agents to vote and reach consensus on a particular value. And that value should be like temperature in London or on a particular day. And we're going to assume that the median vote is the outcome, and we're going to assume that the middle X% of voters get rewarded. And as I said before, the vote is public, so users can see how others have voted, which makes this mechanism kind of silly, but it's useful for kind of showing off how it works. So we're going to identify two potential issues with the system. One is potential reluctance to participate. So agents will just like find it too risky to vote, because each vote costs money, obviously, and you're not guaranteed the reward. So a potential solution we're going to try for that is to use early voting discount, so to make voting early cheaper. And another problem we're going to identify is high prevalence of following the majority, which means that a lot of users, rather than use their own private information, noisy private information about what the outcome is likely to be, they just choose to look at how others have voted and just copy that. And a potential solution for that we're going to use is to use a different reward distribution. So let's see how that actually plays out. So this here is what you can think of as kind of like a dashboard or a UI for like a simulation-like system. And what you have at the top here, the top part here, is the things that are in your control, so the hyperparameters of your system. So they're in your control, which means that you can click and change stuff. And here you have only three hyperparameters exposed, which is what percentage of agents get rewarded, right? So like what percentage of agents near the median get rewarded in terms of their votes. This is the schedule of the voting price, how the vote price changes over time. And this is the reward distribution. And now what we have below here, those are the things that are out of our control. Those are the parameters that describe how our system behaved. So again, this is out of our control, nothing to click here, because when we change our assumptions there, the values here would change, and those are just outcomes of the simulation, outcomes of the behavior of the agents. And as we've said before, we also like to make different assumptions about what it is that agents care about. So in these three columns, we on the x-axis we encode assumptions about what it is that users care about. So in this column, on the x-axis, users are assumed to be increasingly honest, so increasingly likely to behave honestly, which is vote according to their own private knowledge. That's increasing on the x-axis. Here, what's increasing on the x-axis is how likely users are to just follow other users, so kind of be lazy and just copy what everyone else has done. And here on the x-axis, users are more likely to accept bribes. Because we're also assuming that there would be some value that someone offers some bribe for, and users might be incentivized to choose and accept the bribe and vote however someone else wanted them to. And then in terms of the parameters that we observe, for example, this red line here is defined as cluster, and what it says is what proportion of votes were clustered very closely together around the median. And we can see, for example, that it sort of makes sense that as we assume users to be more and more likely to follow each other, then the size of the cluster gets bigger and closer to almost 100%, right? And it makes sense because if users are assumed to be very likely to follow each other, then we're going to end up with all the votes clustered together, and the size of the cluster will be close to 100%. And now in the bottom row, these are the graphs that we're most interested in. So let's zoom in, and what those show is the prevalence of different actions. So there are 5 different actions users can take, and here the yellow line is the action to skip, which means to do nothing. The red line is to follow the majority, which is to vote just how the users have voted so far. The honest is to vote according to users' private kind of noisy knowledge of what the outcome could be. Research means to spend a bit more money to improve your private knowledge. So you can think of it as using your own knowledge is like sampling from a distribution. So doing research would be like decreasing the variance of that distribution. And then finally, the black one, bribe, is to accept the bribe and vote however the person who offered the bribe wanted you to. So here we can see that in this initial setup, the prevalence of action to skip is like dominating. It's around 80%, which means that the participation rate is very low. So users don't really vote at all. They just choose to skip most of the time. And then these graphs show the same thing in a different way, but now on the x-axis, we have the time passing. This is the time passing during the vote. So we can see that when the vote starts, the prevalence of skipping is just 100%. So early on, nobody wants to vote because it's just too risky. And then people only start voting later on when it's close to the end of the vote. And then what happens is we can see the red line is kind of dominating, which means that only then people start to vote, and what they do is they choose to follow what others have done, right? So we have this behavior where nobody votes, and then right at the very end, when some people start to vote, but essentially what they do is just look at how others have voted and just copy that. So obviously that's not something we want because it's not really in line with this assumption of wisdom of the crowds. So now we're going to explore solutions to those two problems: solution to the problem of low participation, and solution of this problem of following the majority rather than voting honestly. So as we've said before, as the solution to the lack of participation, we're going to change the schedule of the vote price. So it used to be constant. It used to be that whenever you vote, you pay the same price. But now we're going to use early voting discount. So what that means, we're going to have the voting price increase linearly, which means that halfway through the vote, you pay half the price. 25% into the vote, you pay a quarter of the price. And we can see how that affected the prevalence of different actions. So if we zoom in, we can see that the prevalence of skipping, so the yellow line, actually is now all the way down at 0, which means that now we have full participation, right? So that's great. So we managed to use the early voting discount to kind of make up for the fact that nobody wanted to sort of start voting first. And now because voting early is cheaper, then agents would be more incentivized to do that. However, what we see now is that by far the most popular action is to just follow the majority, right? So people, even though people vote, the vast majority of them just look at how others have voted and copy that, just because they find it kind of a less risky solution. So now what we could do to try and fix that problem. And as we've said before, we're going to try and change the reward distribution. So the reward distribution so far was uniform. So if this is the distribution of our different votes, right, then at 50% we're at median, and then if you voted lower than median, you're on this side, higher than median on this side. And if we said, for example, that 50% of the users get rewarded, it means that 25% either side of the median, we all get the same reward because it's uniform. So now, if we want to discourage users from just copying what anyone else has done, what could we do? Well, if you're just copying what anyone else has done, then you're quite likely to end up somewhere close to the median. So how about we try and move some of the reward weight away from the median, such that when you just copy what everyone else has done, then you risk ending up here and having your reward much reduced. And we can do it in a linear or a quadratic or a cubic way, moving kind of more and more of this reward weight away from the median. And we can see what happens if we do include that. So now we're looking at linearly increasing the reward distribution away from the median. And if we zoom in on those two, then we can see that now the prevalence of following the majority, which is the red line, has been reduced significantly in kind of both scenarios. What we also see is that the prevalence of skipping has now went up, which means that now we're back sort of to this problem of low participation rate again. And this sort of makes sense because what we've just done really is agents used to have this kind of safe, lazy strategy of just following what others have done and kind of being almost sure of a safe reward. But now we made that strategy much more risky, which means that some agents just decided that they don't really want to vote at all. So what could we do? What could we do now? Because we see that there is this trade-off really between reducing the amount of following the majority and participation rate. So we see that those two are kind of connected, and we can see that this is actually indeed the case. So if we move more and more of reward distribution away from the median, going from uniform to linear, quadratic, and cubic, we can see that the prevalence of following the majority is falling, but the participation rate is falling as well, right? So there is this sort of a trade-off. But as we remember from earlier, introducing early voting discount actually helped with participation rate. So maybe what we can do is to take one of those, like the linear one, and combine it with early voting discount to kind of get the best of both worlds. And if we look here, then this is kind of what is happening. So if we use both of those mechanisms all at the same time, then we can get significant reduction in prevalence of following the majority, but at the same time keep the participation rate very high. And this is kind of this could be the kind of optimal setup that we were looking for. So what we've just shown is the kind of a simple way you could use this simulation tool. And even though this system was very, very simple and kind of silly, because such a vote with public votes doesn't really make so much sense, but still you could see that there are all these potential issues that you can identify, and then for each one of them, all these different mechanisms that you can use to try and fix it. And even here, the kind of design space and the number of trade-offs is huge, right? But and what we also saw is that for such systems, those incentives are really key. Like when you design the system, what's going to make it or break it is going to be those incentives, right? It's going to be those incentives that interact with the real world and determine what the long-term outcome would be. So using iterative design with a simulation tool like Incentivai, what you can achieve is to kind of try out all these different solutions, keep on identifying different issues, keep on finding solutions to them, such that you eventually converge to a solution that you're happy with. And in the end, that's something that we're going to need for kind of widespread adoption, to build those systems that we can trust and that users can trust as well, such that so that they're really widely adopted. So this is the end of this part, and in the next two parts we'll look at some more, probably more interesting and more involved case studies. Thanks. Yeah, and if there's any questions, then.
I just want to add on that when you finally make this thing like completely, it's like you make a bot that can do crypto trading in the real world, like a perfect bot. It's like a side use case to your project.
Okay, I'm gonna think about that.
Because you're creating the agents, right? And second thing, I just forgot my question. I'll talk.
That was the important part.
Yeah, the important part I forgot.
My question is about the rewards, which you have as a, incentive for users behaving. So just imagine a case you have two kinds of rewards. One is money, and the other we just call the good points.
Yeah.
The good points are dependent on how the other actors judge you and your behavior. Is something like this possible in your system? Because this is real social interaction we have in some kind of crypto systems.
Yeah, for sure. So in order to model something like that, we would need to first of all model the mechanism of how these judges are doing the judging, right? So what it is that those people care about. Do they have some skin in the game? Do they have something to win, right? So potentially I would imagine those judges are being paid for something. Potentially they need to reach some sort of consensus as well, right? So what I would do is to have those judges as separate agents that have their own separate agenda and separate objective, and that those agents want to optimize for something their own, and their voting how they vote would be their strategy, right? And then the agents who are voted on, they would recognize that their behavior affects how those other agents vote on them, which in turn affects their payouts, and they would need to adjust their strategy to how the votes happen. So this what you've just described is kind of like adding this extra mechanism, right? And then you need to think about whether it makes sense to have this as like an extra incentive layer where you have like an extra type of agents who care about something else, or maybe you can simplify it and say something like, those agents, they're kind of have to be assumed to be benevolent and vote in a certain way, just to simplify the analysis. So yeah, it definitely can be incorporated, and there are different levels of complexity you can go in.
And with Incentivai, can you also kind of model how people would react or would behave in the case where there's like on-chain governance, how they would vote, is that like, how does governance maybe play in the decisions that a model would make?
Yeah, so governance in general is a bit tricky, because governance in theory can is kind of very open-ended. It can involve any sort of aspect you think about, right? If governance was kind of well specified, so like there are these 5 parameters and you can vote on these 5, then I think this could be something that goes into the simulation, right? Because agents are just aware that at any point in time you can dispute any of those 5 items, and agents can consider those as an option, and if they choose that as a good option, they can take that action and have others vote and so on. But yeah, if you want to have governance as like a general thing and include people coming up with completely new ideas, then yeah, you can't really do that yet. But I think it should be. Again, is this problem of like where you draw the boundary of your system, kind of. Yeah.
Do you have any experience of incorporating sort of socio-behavioral and user preference research into this? So, like one thing that struck me was the results of participation, the skipping, which is intrinsic to the system. So the agents in the system would not have a relative value of time or money as to whether they participate in this system versus another system, and that's really important in the real world. So I know you can go out kind of post hoc after you've developed the model and go and then test it in the real world, but But do you have experience of actually like doing that user research, like saying, well, if the participation level or the participation cost or the reward would be $100 versus $10, would you be more likely to participate regardless of what the other conditions of the system would be?
Okay, so you're asking about doing like surveying users and using that data as the input, as extra input to simulation?
That's right, yeah.
Okay, yeah. So when I work with like actual customers, that's kind of something we do as well. So like when you set up the simulation, again, there are lots of hyperparameters, and yeah, doing surveying users can like at least like I would always be hesitant to like fix any hyperparameter just because some users said something, but they can guide what are the ranges of values we want to focus on. And this is something that that has been done and is very useful because even though I would never trust fixing a hyperparameter, it's good to know which values are more kind of a good place to start. Right?
I have a question about modeling collusion or collusive behavior between agents. Is this something that is possible that you have taken into account in building Incentivai?
Yeah. So there are, again, different ways you can model that. Like the kind of simplest way would be for agents to either have like the same objectives, or like something like trying to like a number of agents trying to optimize like the sum of their objectives. That's one thing. Or you could have agents to kind of share a bit of their strategy policy, so that they can kind of optimize their strategy kind of jointly, and then in that case they could have like a single objective and kind of work together on figuring out the policy in cooperation. So, but yeah, there's lots of kind of research on like multi-agent reinforcement learning and so on. So yeah.
Okay, thank you.
Hi, I wonder how you set the parameters for incentives to corrupt the system or to bribe the system, because is it just based on the assumption that my bet becomes more incentivized if others bet on the same, or how do you bribe the system? Because I imagine this is what you said is I understand it's like a oracle, and if there is a bet behind it, it depends also very much how high the bet is, yeah, and what is the payout of the bet. So this sets the incentive to actually corrupt the system, right?
Yeah, exactly. So again, this goes back to the point that I try not to include any of my intuitions into the system, but rather let the agents be free, right? So a very general approach to including an like adversarial agent would be to say, all right, let's say it's like a prediction market kind of thing, and then this agent in the real world, what would happen? There will be someone who has something to win off chain if this prediction market resolves to a false outcome. So that's something we can encode in their objective function, and then all this agent knows is that I get to win a lot of money, X number of dollars, if this prediction market resolves to a false outcome. But that means that agent would do anything that try and figure out what's possible to do to achieve that. There would be also a limit to it, because we said that they can only win X number of dollars, so they wouldn't do anything like super ridiculous because there's a limit on their budget. But then it's free for them to figure out like the most optimal way to get there. For example, now that they have a lot of money, maybe one way is to trade on the prediction market and actually buy the shares. Maybe simultaneously you can trade the rep token, for example, if it's Augur, the rep token, and try to manipulate the price, right? And maybe there's like a good strategy of combining those two, or maybe they can even figure out something else if there's other mechanisms in the system. So again, all I would say to the agent is say, like, this is how much you get to win if you disrupt the system, and now you go and figure out what to do.
But how do you set this X parameter? That's actually my question. You say there is a maximum outcome of X if
well, that's obviously something we don't know, right? So that's something we need to...
But X can be from 1 cent to thousands of dollars, or even millions potentially.
Yeah, again, so that's your hyperparameter. You want to set a range, try out different values, and see where your system breaks, right? We'll never know.
Okay. Anyone else?
How do you come into account that the systems can be breakable? Like, is that only that systems can trade and vote, or is like can they just modify the node itself and do just you know? Did you get my question?
Yeah. So, okay. So the simulations are mainly about like the economic incentives, right? So, but again, if that what you just described is like another like possible mechanism in the system that you want to give to have at agents' disposal, then you would include it. But the agents wouldn't like try to rewire themselves and try to break the system that way. So it's not quite that kind of thing, right?
Okay.